Okay, so I wanted to give a presentation about Fuzzing Bitcoin Core, and it's mostly going to be, or like the first bigger part is going to be about fuzzing in general, like what it is, why should we do it, what are coverage-guided fuzzers, how do we detect bugs, and like what are best practices when you're writing fuzzing targets. And then the second part is going to be more about fuzzing specifically to Bitcoin Core, like what's our infrastructure, and how and what could people contribute. So my goal kind of is to everybody who is already contributing to Bitcoin Core, or other technical people that are interested in fuzzing. My goal is to get them to contribute or at least run the fuzzers maybe. Yeah. So what's fuzzing? Fuzzing is basically testing code with generated inputs. So instead of like in unit test, you like hard code your test cases. With fuzzing, the fuzzer or the fuzzing engine generates test cases for you. And the most common forms are mutation-based fuzzing, which is given a set of existing samples, like sample test cases and inputs, you mutate those and give those to your program. And then generation-based fuzzing is where you generate inputs based on a model of the input. So for example, if you're fuzzing a C compiler and your inputs are valid C programs, then having inputs generated based on the grammar of C could be a good thing. Otherwise, if you're doing the mutation-based stuff, you're going to get a lot of like C programs that aren't valid C programs. Yeah, and then coverage guiding fuzzing is sort of, I would say, the most popular type of fuzzing. And it's an extension to mutation-based fuzzing, where you have an extra feedback loop, where if you mutate an existing input and you feed it to the program, and the mutated input achieved new coverage or some kind of other interesting characteristic, then you add that input to your input corpus. And you do that over and over again. So you evolve your corpus into like a set of test cases that ideally, cover a lot or most of your program. Examples for coverage-guided fuzzing agents are libFuzzer or AFL++, Centipede. Although Centipede is sort of still a work in progress, but yeah, there are a lot of these out there. And here's sort of an image to illustrate a bit further how these coverage-guided fuzzers work. So you start on the left by picking an input from your input corpus. Then you mutate the input and execute your target. If the target crashes, then you file a bug report and you start from scratch. If the mutated input caused some new coverage or some other kind of signal, then you save it to the corpus and then you start again. So you continue mutating and executing until something interesting happens, a crash, for example. And that's sort of how that gives you that does find a lot of bugs, this technique. So when is this kind of testing useful? Anytime your software takes untrusted inputs, you might want to do fuzzing. That's pretty good for security. If you can test implementations against each other. For example, if you have complicated algorithms that you want to test for like the correctness of those. Usually, like for cryptographic libraries, testing cross implementation is done. For high volume APIs, if you have an API that's like just constantly used with complex inputs, then fuzzing can be good for testing the stability and robustness of those APIs. Fuzzing is not really you can't replace all your other testing, like probability-based testing, unit tests, integration tests. You can't replace that with fuzzing, but fuzzing is like a good additional measure where like your unit tests only execute test cases that you sort of hard-coded, and your fuzzing tests are going to expand beyond that on any sort of random stuff that could happen. Fuzzing is mostly only good if you do it continuously, like it's meant to continuously run 24/7, because otherwise if you write your fuzzing tests and you don't execute them, they're basically useless. So here's an example for libFuzzer, which is a coverage guiding fuzzing engine. And the example target I have in this little example here is the parse.json function, which takes a string and expects that to be JSON and parses that into this in-memory JSON object. And with libFuzzer, we define this function, LLVM fuzzer test1 input, which is the entry to your fuzzing target. And then data and size represent the generated test case as a byte array. And all you do here is pass the data from the fuzzer straight to the parse.json function. And then, the fuzzer keeps mutating and executing the target. Interesting inputs are added to the corpus, and then you go again and again until there's some kind of crash. And the fuzz targets for libFuzzer are usually instrumented at compile time with stuff that helps libFuzzer make smarter mutations. So for example, one of those instrumentations is that for every compare instruction that your program does, libFuzzer will have a little hook into that and observe the compare instruction. So, and it can use the values for those compare instructions to inform the mutations it makes. And the same goes for mem compare or string compare when you're comparing specific strings or memory. So that's sort of how this helps libFuzzer sort of magically guess special values that you have in your program to insert those into the inputs. And I mean, maybe this is too much, but I would recommend looking at the code of libFuzzer. So I have the link in the slides here. Sort of help me demystify a little bit how these fuzzing engines work. And it's not too crazy. It's pretty straightforward, I'd say. All right. So again, if we look at this example, it's only going to catch a certain type of bug. It's pretty superficial. We just pass the data into the parse.json function, and the only type of bug we'll catch is if something crashes. Now, when checking for other types of bugs, logical types of bugs, is much harder. Again, if we compare this to unit tests, we specifically hard code our test cases. If we put in input A, we expect B to happen, or stuff like that. So you are basically, if you're writing unit tests, you are the oracle for deciding when something is a bug. But with fuzzing, you don't really have that, because you're not specifying the inputs. So you need some kind of bug oracle to tell you, hey, if I pass stuff into my function, did a bug happen or not, basically. So I have a list of, a non-exhaustive list of things that you can do or use as bug oracles. And the first thing here are assertions. If you basically, in your code, if you place plenty of assert statements for assumptions that are internal to your code, then if, on some input the fuzzer provides, one of those assertions hits, that should be a bug. Another thing is resource limits. Maybe your targets have you have a specific requirement for how long something should execute or how much memory at most it should use. And if those assumptions are violated, crash. It's another oracle. Then I think one of the easier and biggest things, at least for C and C++ fuzzing, are sanitizers, which are able to catch a bunch of C or C++ specific quirky behavior, like undefined behavior or data races, reads on uninitialized memory, detecting out of bounds reads, heap overflows, stack overflows, use after freeze, all this sort of really weird memory unsafe stuff that you can have in C and C++. Then another thing you can do is have function inverse pairs. So encode, decode, encrypt, decrypt, or if we go back to the example with the JSON parsing, you could parse the JSON and then re-encode it into a string and check that the results are the same. It's sort of similar to differential fuzzing. In differential fuzzing, you have two implementations of the same thing, and you basically pass the input to both implementations, and then you check that the result of these is the same. So I think I mentioned this in the beginning as well. For cryptographic libraries, this is typically something you can use. If you have two implementations of, I don't know, SHA-256, you fuzz both and check that the result is the same. Another technique are null space transformations. These require you to have control over the type of mutations that your fuzzer makes. And not all fuzzing engines support that, but some do. And basically, the idea here is that you only make, like, you have an initial set of inputs that, do something that you specifically want them to do, and then you only make mutations that to preserve the semantics of those inputs. So, for example, if you're testing a compiler, you could like replace every occurrence of x with these like x times 1 or x plus 1 minus 1, and the result, like the behavior of the program afterwards, should still be the same. And then the last thing, which is a bit generic, but domain-specific checks, like have checks specifically for the type of application that you're fuzzing. So, for example, in the Bitcoin context, if you're fuzzing block validation, you could have a rule that says a Bitcoin block that's valid under some soft fork rules should also be valid if we're not enforcing the soft fork. Otherwise, it wouldn't be a soft fork. Okay, so let's move on to best practices for when you're writing your fuzz targets. One thing is that you want to avoid any sort of crashes that aren't actual bugs. So if you have extra test-only code for your fuzz targets, you should make sure that that test-only code doesn't crash. Otherwise, you're going to get a lot of like false positive bug reports, and those cost a lot of like engineering effort. So the best thing you can do is just write tests for your test utilities, and expect that the input the fuzzer gives you is, can be malformed and don't have any specific requirements on the input. The next thing, you should verify coverage. So if you're fuzzing something, then make sure that, after you've written the target, that the fuzzer is actually able to reach into the part of the code that you want to be fuzzed. And a specific example where this could not be the case is if there are like checksums or encryption or compression. Like these things, a fuzzer cannot magically guess or get right. Like if your program requires a signature, then your fuzzer can't come up with a signature for some random public key. So in those cases, you need to work around blockers like that to make the fuzzer able to actually get to the code that you want to fuzz. Another big thing is determinism. So given the same input, your target should always behave the same. Otherwise, it's really annoying if you like have a bug, you have a crash, and then you try to reproduce it. You take the input that initially crashed the target. But then all of a sudden, because your target is not deterministic, the crash doesn't happen anymore. So that's really annoying because it costs more time to figure out what the actual bug was. A couple of things here is you should avoid actual randomness. Like if you feed, for example, entropy from your operating system to your program to get some sort of actual randomness, don't do that. And when you're fuzzing, like mock out the randomness or use fixed seeds. Also avoid global state, which can cause determinism issues. If you're using global state, reset it after each iteration. Like at the end of your target, reset the global state, or ideally just avoid global state entirely. Another thing is make sure your targets are fast. Fuzzing is basically a search for bugs, and the faster the search, the better. There's a benchmark in, like Google has this fuzzing repository where they also outline, a bunch of stuff about fuzzing, and they recommend 1,000 executions per second for your targets. One recommendation here is that, if you have a slow target, maybe it's doing some sort of expensive I/O, which you should avoid, like reading or writing from disk. I guess if, it could be that your target just is inherently slow and you can't do anything about that. In that case, if you have the infrastructure to scale it up, where like you just keep adding CPUs, that could work, but ideally, try to make your targets as performant as possible. And the next thing is keep the scope of your target small. So what I mean by that, don't try to fuzz like a huge amount of code, but just try to direct the fuzzer into like interesting areas of your code where you might think there are bugs. So if you have a really large RPA, consider instead of fuzzing the entire RPA, just fuzz like a subset and put those subsets into different targets. and mock out any components that aren't under test. And like fuzzing, if you're thinking about how to write fuzz targets, I find it sometimes useful to first think about if you were auditing the code manually, just by reviewing it, how would you go about that? And then write your fuzz target in a way where, you know, the outcome, or like try to write your fuzzer such that it audits the code like you would, sort of. Yeah, again, here's a link for the Google fuzzing docs, which have also more stuff on best practices. Yes, Stefan?
I had a question on I think the previous slide, if you just go back one.
Yes.
So when you say avoid non-bug crashes, I'm just a bit confused because I feel like it kind of goes against another principle of, you know, failing explicitly to avoid like hidden bugs. For example, if you have a function that expects, you know, the integer to be between 1 and 100, then you could write the search statement to check that. But you're saying that goes against, you know, writing good fuzz targets, unless, of course, you don't fuzz that function directly, but you make sure in the function that calls that function, you do input validation and kind of handle that gracefully. So if you then target the kind of the parent function or the call side, then you're fine. So are you saying like avoid those kind of assertions everywhere, or only in places that you expect are going to get fuzzed? I just feel like there's some kind of tension there.
Yeah, I would say, okay, personally, I don't really like assertions like that, because if you're using that function, you have to know about the assertion. And the more you do that, the more you have to know about these assumptions. But if you have assertions like that and you want to write a fuzz target, then you can pass the input the fuzzer gives you in a way such that you only pass the correct range, you know, in your example of the integer, for example, to the function. But yeah, if you write a fuzz type for a function, you should avoid, and you know about the assert, you should avoid hitting that assert because it's not an actual bug. Did that answer your question?
Yeah, I think so. Thanks.
Okay. Oh yeah, actually, if anybody now has questions about fuzzing in general, all the stuff I said, or anything else about fuzzing you've wondered, maybe now is a good time, because after this, I would talk about Bitcoin Core specific stuff. Okay, then I'll move on. If in the end you have questions, feel free to bring them up. Okay, so Bitcoin Core's fuzzing infrastructure, we currently have 195 targets, and our input corpora are maintained in the QA assets repo. I think the biggest contributor to our like CPU is OSS Fuzz, which OSS Fuzz is like a cluster fuzz instance managed by Google to support notable open source projects. And cluster fuzz is basically just a infrastructure tool that, you know, allows you to fuzz at scale, where I think the entire cluster that Google is managing is like 100,000 VMs or something, where all it does is just constantly fuzz various projects. And I have some stats here where like OSS Fuzz, as of January 2023, there were like 8,900 vulnerabilities, 28,000 bugs across 850 projects. So this sort of speaks to the usefulness of fuzzing. The only downside to OSS Fuzz for us specifically is that they have a 90-day disclosure deadline. So if OSS Fuzz finds a bug through our fuzzing targets, then it at first discloses them, you know, in secret or in private to the maintainers. But then there are 90 days, basically, you know, we have 90 days to fix it, or they disclose it. There are some exceptions, but this rule has, you know, in the beginning, people were against adding us to OSS Fuzz specifically because of that rule, but we've been on there for a while and we haven't really had problems with this. Then, you know, contributors also run their own infrastructure on fuzzing. It's kind of hard to quantify how many CPUs that adds. Judging by the amount of contributions we get to our like corpus repo, QA assets, it's probably not that many people, or they're not contributing the seeds back. one reason for that could be that it's not super easy to self-host good fuzzing infra, because you have to like maintain that the fuzzing stuff is still running. You have to merge the corpuses and then contribute them back to QA assets. So it's like a whole hassle to do all of that. So it's not super surprising that we don't see a lot of that. Yeah, coverage reports for like how much of our code is coverage. I have 2 links here if you want to later check that out. We additionally, to continuously running our fuzz targets, we run them in our CI just on the existing corpuses that we have for our targets, and that just serves as like a regression test. But those in the CI itself, we do not generate new inputs, so it's not doing actual fuzzing. It's just executing the inputs that we have to check that everything is still working. And our like fuzzing framework is fuzz engine agnostic, meaning you can pretty much plug any fuzzing engine into it that has the same interface as libFuzzer, like a byte array. libFuzzer, AFL++, HongFuzz, and probably a bunch of others. And then I also included Marco as part of our infrastructure here, because he has been, I think, from the beginning, like before we even had fuzzing, he's like the main driver, I think, behind our fuzzing infrastructure. So he's a key part, I would say. And something that's on my wish list, or maybe wish list, which we currently aren't doing, we could have our own cluster fuzz instance. The downsides of that would be obviously that that has to be maintained. The upside would be that we can basically throw money at fuzzing and increase the number of CPUs that are fuzzing our code at not that much effort. So, okay, so here's an example of how you can fuzz with libFuzzer. So you need to build Bitcoin Core specifically for fuzzing. And for libFuzzer, you need to use Clang and add the fuzzer sanitizer while configuring. And then if you're running libFuzzer, the fork mode -fork and then the number of cores that you want to use is pretty cool, because it lets you fuzz on multiple cores. And it already includes a merge step, where if you just normally run libFuzzer, it'll like keep adding inputs to your corpus. Just anytime something interesting happens, it keeps adding them, but it doesn't minimize the corpus. But with the fork mode, you actually, that results in a minimized corpus, because it keeps spinning up new jobs that run for a while, and then they merge the new inputs from those jobs into the base corpus. You can start with an empty corpus, or you can download a corpus from QA assets and continue building on that. The target you're trying to fuzz is specified through the fuzz environment variable. So this is sort of one quirk of our fuzzing infrastructure, where all the fuzz targets are compiled into one binary, and then you select which target you're executing using this environment variable. So for example, the process message target that I'm fuzzing in this example is fuzzing the processing of one singular P2P message. Yeah, if you want to see all that, like if you want to list all the targets, I have this in the slides here, like print all fuzz targets in the board. And that'll just give you a list of all the fuzz targets that we have. Depending on which sanitizers you're using, you should look at our sanitizer suppressions. There are a couple of instances in our code or dependencies that we have that are like false positive warnings for these sanitizers. So yeah, if you are fuzzing with one of these sanitizers, then you should use the suppressions that we have. In general, if you want to see more about fuzzing with certain fuzzing engines, we have a fuzzing doc in our documentation, also linked in the slide. Okay, so once you've run the fuzzer, let's say again for the process message target, and you want to contribute any new inputs you found back to our QA assets, then you need to run a merge step with libFuzzer. You can see here with the dash merge = 1. And then you specify the QA assets corpus directory, which it's QA assets / fuzzy corpus / and then the target name. And then the next directory you specify is the directory you used for fuzzing. And this will basically merge any, like copy any inputs from your directory to the QA assets directory if it causes new coverage. And then you can, it's a repo, you can just open a PR adding the new inputs, and any new inputs will add as, regression tests in our CI, or they will help if people are using our QA assets corpus as a base for their fuzzing efforts. It'll help them, have more coverage from the get-go. And collaboratively growing a corpus in this fashion accumulates the work that has been done on fuzzing in total. Yeah. All right, now sort of a call to action. If you want to contribute, the easiest thing you could probably do is run the fuzzers and contribute the inputs back to our corpus. If you do find bugs, sensitive bugs, please report them to our security mail. You can also see the security doc in our repo. If you're not sure if it's a security issue, still just report it to the email. You can write targets for code that is uncovered. For example, our wallet has pretty poor coverage. I think only I think coin selection has a fuzz target, but that's about it. Yeah, then another thing, you can improve our bug oracles. Like, we have a lot of targets that sort of simply throw input at our code, but they don't really have any sophisticated bug oracles. So if you think back of the slides I had on bug oracles, just if you see something where one of those concepts I outlined applies to us, please contribute that, and enforce best practices. If you see a target that's slow and you find a way to improve the performance, for example, then please contribute that. Okay, yeah, that's pretty much it. Here's a link dump with like fuzzing resources, blog posts, videos, documentation. Yeah, thanks. Yeah, Fabian.
Actually, I just want to clap first, but it doesn't matter. I also have a question. So there's like I've seen over the last 2 years like a lot of fast targets being added, and it's kind of a good practice to just whenever you develop something that is roughly just makes sense to add as a fast target, it typically is added as a fast target. But then, like, I recently thought, okay, does it really make sense to have everything, like to test everything with the same power, basically? Or is there maybe already some kind of discrimination between the different fast targets so that we have some that are more critical, that we run more often, or we prefer them, or we exclude them in some cases? Like, is anything being done in that direction?
I don't think so. So as far as I'm aware, OSS Fuzz is our biggest contributor in terms of CPU, and I don't think they have any sort of prioritization for what you're mentioning. I mean, I would think that would probably make sense. Personally, when I'm running fuzzers, I specifically like either write my own targets or go for the targets that I think might be interesting. But yeah, it's maybe a thing we should figure out how to do it. Any other questions?
Niklas, I have a question.
Yes.
I'm curious if someone want to run this fuzz testing themselves, how does that contribute in terms of like the determinism? Like, if I was running it, I would like how would I be running be different from what someone else is running if there's this like determinism piece of it?
Okay, yeah. So the determinism, what I was talking about is the target itself. So the code you're trying to fuzz should be deterministic, but the fuzzing engine itself could produce, or they all have some sort of randomness when they decide to mutate. So the more CPUs you add, the more sort of combinations of possible inputs you can explore. Yeah. So the more people are adding CPUs and contributing to the corpuses, like that would be useful. Did I answer the question?
Yeah, thank you.
Okay. Stefan?
So the code execution path depends on the compiled binary, right? Like on different platforms and based on your environment, like you can have different execution paths. So given that when you're building the corpus, you're looking at how different inputs trigger different paths. Does that mean that we have different corpora for each binary, or like how do we account for that? That it depends on which platform that you're running on, which code gets executed, and potentially how the program behaves.
Wait, I'm not sure I understood your question. Is it that depending on the platform that Bitcoin Core is running on, different things might happen, and you're wondering how we incorporate that into fuzzing? Or like
yeah, so for example, on Windows or on Linux, oftentimes.
I can't hear you anymore.
Sorry, I have some microphone issues sometimes. I should be back now. Yeah, so on Windows and Linux, we oftentimes have slightly different execution paths, which I can imagine should affect fuzzing. So how do we deal with that?
I mean, okay, so I know that OSS fuzzes on different architectures or operating systems. So I think Windows, macOS, Linux, those three are definitely included. But yeah, the only solution I see for this is running on those different architectures and operating systems if you want to get the whole coverage basically. And then okay, if you run on Windows and then you contribute back to our corpus, I don't really know how the corpus deals with a mix of like inputs for different architectures, but it probably doesn't really matter. I don't know.
Because it actually kind of ties into another question I had. Like when you submit your new corpus back to the QA assets repo, how can someone check that this is not just someone spamming the corpus with a whole bunch of new inputs that don't actually add anything? I feel like there could be, and I have no idea how it works. Maybe I'll just ask that first. Like, how does that work? Can you do some spam prevention checks or?
Yeah, so I think I'm not sure if the merge step is deterministic, like the merge step of libFuzzer. But one thing you can do is check that the coverage from the old corpus is smaller than the coverage from the PR where the new inputs are being added. So only merge something if new coverage is added, basically. Should probably prevent spam. I mean, if the spam is increasing coverage, then I guess it's good spam. Yeah.
Well, but if it's just mutating, an input from say 1 to 2, but it doesn't trigger any new code execution paths, then that would not raise any flags, right? That would get merged without issues, even though it may not be triggering new paths.
I mean, ideally, whoever is reviewing the PR checks that the newly added inputs do increase the coverage. And then, if, say, the mutation from 1 to 2 doesn't cause new coverage, then you don't merge that. Basically.
But so this is then where the platform question comes into play, because maybe on one person's machine, it looks like it's a safe code path. On another person's machine, it doesn't, which makes it a very potentially laborious process. It's probably not that critical, so I don't want to go on too much of a tangent. I was just wondering how that gets dealt with.
Yeah, I don't think we deal with that.
Okay, so far so good.
But yeah, the maintenance of the corpus is important in itself. But I mean, we haven't really had spam or I don't think we've ever had issues with like different operating systems and stuff. Yes, Stefan.
Sorry, I've always. I'm not sure if you already covered it. I was briefly distracted for a minute, but I was wondering, so a lot of the time is spent on building the corpus, mutating the inputs, trying to find either crashes or new coverage paths. So I think retrying the existing corpus is probably a pretty quick process. Do we run those tests, for example, during CI already? So not finding new inputs, but running existing ones. Like, how do we use those at the moment?
Yeah, so I did mention that in our CI, we do run all the fuzz targets and give them the inputs from the QA assets repo as a form of regression testing.
Right. Okay. And is it like a long test? How long roughly does it take? Is it like in minutes?
Oh, I don't know the exact time, but depending on what sanitizers you're using, or if you're running that with Vagrant, it can take quite long. I think the Vagrant job takes hours, or I think Marco said like 12 days on some old computer he has. So that we obviously don't run in the CI, but yeah, just it depends on the target, the input sizes. Yeah.
Oh, okay, cool. And
but I think like in our CI,
data.
it should be like half an hour, maybe, would be my guess.
Okay, that makes sense.
Yes. Whoever wants to go first.
A side note about different platforms code execution path. It often related to input-output operations and system level operations like getting random number, and all this stuff you already mentioned should be avoided during fuzzing.
Yeah,
so,
right. Yeah, so mostly it's probably not an issue.
Yeah, that was my note.
Okay, yeah, no, that's a good point. Okay, Stefan.
So I'm guessing, I mean, fuzzing usually happens across a large call stack of functions, right? You don't want to do it on like the unit level test. You want to ideally have test a bit more end-to-end, I think. So does that mean that you also mostly want to point your fuzz targets at more the outer layers and like the user-facing layers where you expect the user input to come in, or not necessarily? I'm just trying to find good heuristics on when to do fuzzing.
So one thing I think I mentioned is like you should try to keep the scope of your targets narrow. So like in Bitcoin Core, for example, if you're fuzzing the P2P, our P2P code, then currently like the validation engine is attached to that, maybe the connection manager even, then all the P2P code, all the components in the P2P code, and that all adds up to a lot of just a lot of code where the fuzzing engine is not going to be super efficient at like exploring all of that. So one thing you could do is like mock out the validation engine, for example, so that you specifically you should try to point your fuzzer to the areas where you want it to fuzz instead of just fuzzing everything. That's not gonna that'll not be super efficient.
No, that's fair enough. I think I was more just thinking on lines of if you're trying to prevent like buffer overflows, that's usually like people trying to feed edge cases in terms of input data. And so if you're covering those functions, then that seems like an important place to start, perhaps.
Yeah, but okay, yes. But for example, you could fuzz our connection manager, which handles like the networking part, and our peer manager, which does message processing. You could fuzz those independently. So you don't need to feed, let's say, messages into the connection manager, like fuzz all of the logic there, and then also have that passed on into peer manager so that the logic in peer manager is also executed. You should just have two targets, one that's fuzzing the message processing code and one that's fuzzing the networking code in connection manager.
That makes sense.
That would be at least my thinking about it. Otherwise, yeah, I don't know. If the scope is too large, if there's too many code paths, too many branches to take, it's it's not going to be super efficient.
Yeah, that makes sense. Thanks. I think those were all my questions.
Yes, Mike.
You mentioned that Google provides a cloud version of this with the OSS Fuzz project, which seems to use this cluster fuzz underneath. And it looks like running cluster fuzz is easy, potentially on Google's cloud provider. Probably you could redo it for Amazon or whatnot. Is there anybody working on that? I know that was part of your wish list. Are you aware of anybody who's gone down the path on that?
Not that I know of. I have that in my like to do, but it's pretty much yeah, it's pretty far down in my to-do list because it's kind of a bigger project and requires a lot of work that I'm not sure if I necessarily want to do, like maintaining infrastructure and making sure that it all works and stuff. Like if you look at the OSS Fuzz project itself, it does require a lot of maintenance. Obviously, we wouldn't quite be at the scale that OSS Fuzz operates at, but I still think it would probably require one person working on that, maybe part or full time. So
yeah, I think I saw running 30,000 VMs or something like that.
It's pretty crazy. But ideally, I think we should have. I mean, yeah, again, it's hard to quantify how many CPUs or how much CPU power we have behind our fuzzing, but we should probably be like have more than what we have right now. And we kind of, at least from my perspective, OSS Fuzz seems like the biggest contributor. So we are relying on sort of Google donating CPU to us.
More than we have now, meaning more than the OSS project is allocating for the project?
Yeah, as far as I'm aware, they are giving us one CPU per target per sanitizer. So I think like 1,000 CPUs maybe, which is, that's not bad, but the more the better, I think.
Is this something that you see that new contributors are interested in or familiar with? It would seem like somebody who's got, I don't know, DevOps background or whatnot would maybe be interested in like parts of this. Obviously, they would have very little familiarity with the Bitcoin Core code base, but I'm just wondering if that's interesting to younger developers, if you see any uptake in that.
Not probably the answer is no. I think we have had one Summer of Bitcoin student who worked with Marco on fuzzing. But yeah, I wouldn't say there's a huge uptake in new contributors. I would like to see that, and I think fuzzing is pretty cool, but it's a bit of a mysterious field maybe still. Like for example, I didn't have a fuzzing class in university, for example. Like we did have stuff on software testing, but fuzzing was not included in there. So